So the final coordinate system that we deal with is in curvilinear motion is cylindrical coordinates. And cylindrical coordinates are to a large degree the most non-intuitive form of the equations that you deal with. So if I look at something like here, I have a curved path that's sort of crazy curved, and I define a position P, which is defining where the particle is at this instant. I define it with respect to both r and a theta right there. And r and theta will tell me where everything is. But in essence, I can say r is really r in the direction of u sub r. So u sub r is here, and u sub theta is here. And if I go to another position, my r and theta are going to change, and u of r and u sub r and u sub theta are also going to change. But there they are. They sort of track along with the particle. I've chosen 2 points that look like they're almost parallel, but you can see that, for example, if I put a particle over here, it's sort of ur would still go out this way, and u theta would go like this. Velocity at any point still tangential to the coordinate system, so velocity is the derivative, so it's going to be r dot ur, r ur dot, or velocity is equal to r dot ur, r theta dot u theta. And if I do that, I get Vr this is my v sub r, and this is my v sub theta. Now, I'll talk about how I got this term. I did a different approach than I did in the NT coordinate slide, but just for the sake now of just getting all the equations onto one slide, here you go. If I take the derivative of acceleration or velocity, I get acceleration, and that's going to be r double dot. Remember, double r dot is dr dt. R double dot equals second derivative of r t. And same thing for whatever variable I'm interested in. R double dot in ur direction, r dot ur dot, r dot theta dot u theta, r theta double dot u theta, and r theta dot u theta dot. So I have all of these terms that have appeared in my expressions, and I can write out my acceleration, which again, I haven't really talked about this one or this term, but in the end, bear with me, it's going to be more details on the next slide. Acceleration r is acceleration is acceleration r in the r direction, the acceleration theta in the theta direction, and acceleration r is r double dot minus r theta dot squared, r theta double dot plus r theta twice r dot theta dot equals acceleration theta. This expression is something you need to remember, and it's something, again, with all of these things that I'm putting in boxes, the idea is that you might want to put these on your crib sheet as you go towards the midterm and final exams. Magnitude, acceleration r equal to ar squared plus a theta squared. And again, this is sort of graphical picture of that. So last time I did sort of this thing where I said, well, look, the limits is 1 over rho is this derivative with respect to position of the path variable, or the path unit vector. But let's look at it from a Cartesian coordinate. So the radial unit vector could be defined this way with u sub r, which is magnitude 1, with a theta here. And so if I take ur, it's cos theta, sine theta. If I take its derivative, it's theta dot. Okay, that's going to be useful. But minus sine theta plus cos theta j. Hey, that's an orthogonal term. That's normal. And they're in the u theta direction as opposed to the ur direction. So ur dot equals theta dot u theta. And so you're getting that out of this, and this is kind of a neat result for what you're getting in terms of looking at this. And just a really quick picture, tack u theta, and make this nice normal direction. And you can do the same thing, and you find the same sort of result for u theta dot, and you find that it's the negative of theta dot ur. So out of this, you get a set of equations that eventually are going to be more useful when we look at angular motion, But unlike the NT coordinate, the big advantage here is that I know where the position of the particle is with respect to an origin. So if you need the positional reference and you have curved path motion, often you may be looking at a cylindrical coordinate system to solve.